but also a dynamics associated to the inorganic framework, and it's described by this passive transition. So what I'd like to do here is just to put in perspective the three compounds of this family, and to think about how the size of the framework can influence the dynamic behavior of these three compounds. Also, I'd like to think about how the size of this framework can favor one type of dynamic over the other. So, in the methylammonium chloride, we've seen that there's actually no acoustic phonon softening, but there's an order disorder transition, and we can think about this as in this compound. It shows the smallest cage size, which means that the hydrogen bonds are the strongest in this system, and the molecular cation thus becomes the more rigid unit in this system. So when approaching the transition, both tilting or distortions of the octahedra and the order disorder transition of the molecule become incompatible, and this forces the structure to distort. So in this case, the order disorder transition is favored in this compound. In contrast, in the bromine and iodine compound, there's a bigger cage size, and actually it has been shown that in the bromine compound there is a clear phonon softening in addition to the order disorder transition, and this has also been shown in the iodine compound. So I'm going to conclude. So what I've showed is with the temperature dependence of phonons in this system, we've shown a coupling between two different dynamics in this system that is associated to the inorganic framework on one hand, and the molecular dynamics on the other hand. Also, what I'd like to emphasize in my last comment is that we've seen the presence of acoustic phonon broadening in both hybrid systems and all inorganic systems, and this was thought to arise from the A-side fluctuations. I've also said that this fluctuation may affect the thermal transport in this system, and recent studies have shown that both systems actually show similar properties for photovoltaic efficiency. So this would make us think that this raises the question of how important is the molecular nature of the A site for these photovoltaic properties, and I think this is an interesting aspect to further investigate. So thank you for your attention.
Questions? Okay.
Nice presentation. Have you seen any results or indications in your experiments of interaction with domain walls? There should be ferrostic walls at the first phase transition, and at the second, again, new walls might appear. Do we know how big are the domains, for example?
So we've done some diffraction measurements from a single crystal, and indeed we've seen a lot of domains, the appearance of a lot of domains. The data is still being analyzed, but this is difficult. These are pretty difficult to analyze actually, because we don't know how to characterize these domains, except we just see a lot of bright peaks, and so we're trying to further study detailed temperature dependence of these domains.
Pardon me.